Webworks up now, one on area, volume, and mass, given a density function. There's some stuff up to practice with that. There's also a polar coordinates one up that's gonna make a lot more sense after today. We talked about the intro to polar coordinates, but oh geez, okay, that's why I put that there, so I remember. So let's actually
Just to remind you.
What's that?
Just want to remind you.
Thank you, thank you. I appreciate that so much. Let's see. Boy, if I don't bring my own pens, I guess we're screwed, huh? They don't send me any pens in this room.
There's some pens over here.
We're at, over there?
Yeah,
Okay.
I don't know if they have any ink.
They're probably low quality.
Yeah.
Yeah.
There's something if you forgot them.
I think I'm good. I'm good. Thanks, though. Thanks. Appreciate it. All right, let's take a minute. Let's just let this bell bring us into the class. Good transitional. Transitional. Ritual. All right, sitting up straight. Coming into your body. Just feeling all of it at once. Hearing all of it. I think I can almost still hear it, just a little bit. It's hard to tell if you're still hearing it or you're just hallucinating, you know, like just imagining that you're hearing it. All right, very good, my friends. So, onward. Get out my notes to make sure. Got some cool examples. I got a cool integral we're gonna do today. Let's actually warm up with a few things, with polar coordinates. So, if we were in rectangular coordinates, and I asked you to sketch x equals a constant, what would that look like?
Just a line.
Just a vertical line, right? This says that take all the points whose x coordinate is k. So for k here, get a vertical line. And if I said y equals some constant, what do we got?
Horizontal.
Horizontal line. Y equals L there. Now let's look into the polar plane. In the polar plane, we've got r and theta. I can't label the axes. It's helpful to have these axes, but we can think of those as kind of the compass points. They're definitely helpful for navigating around. So here's theta equals 0 rad. I was like gonna say degree and then radian, and it kind of got weird. There's theta equals pi half. There's theta equals pi, and then theta equals 3 pi over 2. So what if I asked you to sketch, that's a sub-zero there, not a 6. What does that look like?
Circle? Or
Is it a line?
It's a straight line at a certain angle.
A straight line through the origin at a certain angle. It's saying all the points are theta, whose theta is fixed. So that means once we can identify what angle theta represents, it's all the radian. Now this here is positive. Here's r equals 0. And then this would be r is negative back here moving in the backward direction. So that's one of the things. Now Christian, now this one. Now what's that? That's a circle. So when I have the radius fixed. So that would be a circle of radius fixed radius are not. So now think about over here, when you think about a piece of grid paper, when I think about what are the geodesics of the Cartesian plane, it's all the horizontal lines and all the vertical lines, and it gives me a sense of kind of how to navigate in this space. And when you think about what are the little elements we've been using for integration, we've been using tiny little squares, right? We take our shape, take our weird ass shape, and we cut it up into a bunch of rectangles. And we use rectangles because these are the natural shapes defined in the plane from lines that have constant coordinates in one of the coordinates. Now over here, what am I going to get when I think about the natural geodesics? So I'm writing this word up again, but it's just such a great word. It's like, what is the lay of the land here? What would our map look like? And it's going to be different fixed radii like so. So this is a bullseye. These are all the constant radius curves. I mean, there's infinitely many, right? But this is a representative. And then I've got, wow, imagine I did it well, but I've got all these spokes which represent where theta is constant. So the geodesics in this coordinate system look like this, kind of like a bullseye, or what is it, a dartboard kind of thing going on there. These were squares. These guys are a little bit different. So what we're going to focus on today is if I have some weird polar region and I want to cut it up into polar squares, polar rectangles, what is that going to look like? And what it's going to look like is a bunch of shapes that look like this. This is going to be the rectangles we cut things up into if we're thinking polar coordinate-wise. So what we need to do is, over here, this was pretty straightforward. If we had a slight change in x and a slight change in y, and we looked at our Riemann sums, there'd be some star. We would have delta x, delta y, and that was our area element. What is the area element going to be over here? And it's a little bit more complicated, but it also creates this kind of cool effect where some things that we couldn't do there, we can do here, and of course the vice versa always holds. So let's take a look at the area element in polar coordinates. So I got to redo my picture, and I'll just do it over here. All right, so let's say I've got a certain theta sub k. So I'm cutting the plane up into different spokes, and that's theta sub k, and then I've got theta sub k plus 1. I'm just making these cuts up so I can get some finite things going on here, things I can deal with. And then I've got these circles that go like this. And we'll call this r sub k, and we'll call this r sub k plus 1. So imagine that I'm cutting up something into different radii, and I'm cutting it up into different spokes, and we're just going to focus on this one for a minute. And what we want to do is figure out what is the area of that shape. So we're going to do a little magic here, a little work, and we have to kind of think this through. And I want you to be able to kind of reproduce this on your own. So first off, let's start very simply. This region is actually, first off, a circle. It's part of a circle of radius k plus 1. That's my bigger radius. And then I'm subtracting a circle with a smaller radius. So let's say that that's r sub k right there. And I'm trying to make them look a little smaller. But this piece right here, if I carried it around, it's called an annulus. and it just means a ring. I want to be able to figure just first off the area of this, and then we'll figure out what portion of it's inside that little critter there. What is the area of this? What's the area of that? Guess I better get some tea. Oops, sorry, Daniel. Yeah, pi r squared. There we go. We're getting it together. I know we know that. I think we're afraid to say it.
I always mix it up with 4 pi r squared.
That is the surface area of a sphere.
Is it?
Yeah, and I now you're getting me off on it. I was kind of wanting to talk about that, but well, let's not. So the area of this is pi r sub k plus 1 squared. I think we're ready to get the area of this one now. What's the area of this one?
Pi r k squared.
Yeah, thank you. With pi in front. So this ring here, this full ring that I'm talking about, is going to be the difference. Let's call that k plus 1, and then that sub k. So a sub k plus 1 minus a sub k is, I've got a pi that they share, and then I've got rk plus 1 squared minus r sub k squared. You see what I did there? Just a little bit of algebra. Just factoring out the pi, because that's going to be helpful in a minute. And I'm going to do one more thing here, and that is I'm going to rewrite this as pi times, how does this factor? In my real analysis class,
It's the difference of squares.
it's the difference of squares, right on.
Yeah, RK plus 1 plus RK times RK plus 1 minus RK.
Love it. Nice. Thank you. Beautiful. We've got that shit down. So notice that this right here looks like the delta r. So that's the change in the radius from one to the next. So we're going to call that delta r sub k. And so this delta r sub k is just this difference here. Like that. And so we rewrite this as the change in those annular area, and we still have to whittle it down to that little wedge, and we'll get there in a second. But this is going to be approximately, or exactly, r sub k plus 1 plus r sub k times delta r sub k. Okay, so that's just the annulus. That's just that whole ring. Now we gotta figure out how do we get a portion of that little piece of the pie that's coming in like this. So let's think it through, kind of reason how we're gonna get there. So let's think slowly here. If I had, let's see, what is the angle? Well, hold on. Let's start with a circle. There we go. Start with a circle. We know that, sorry, I'm trying to get my bearings here with the words that I want to say. Yeah, I guess I just want the portion of the area that's between two pieces like this, but we're going to get there slowly. So what is the full area of this? If I'm at radius r, we know that that's pi r squared. What is the area of half of it? Pi r squared over 2. So the area of half of it is pi over 2 r squared. Let's get another picture here, because we want to see if we can come up with a rule. And what is the radian measure of that angle right there? That's just pi. So when the angle was 2 pi, let's actually make a little table here. So angle versus area. So when the angle was 2 pi, that's the full circle. We get pi r squared. 2 pi. When the angle was pi, we said that, oh, well, that's just half the area of a circle, so that's pi over 2 r squared. When the angle is pi over 2, like this, what's my area? Pi over 4. It's half of this area here, right? So we're not doing anything super profound, just taking proportions here. But when that angle is pi over 2, then this is pi over 4r squared. Now we're starting to maybe see if we can come up with a pattern. So if I make this angle theta rad, how can I move from here to here? What did we do to move from here to here? Like what, besides the r, what happens to this number in front? How do you move from here to here?
Divide by 2.
Divided by 2, divide by 2, divide by 2. So it looks like we're taking half the radian measure times the radius squared. So this would be 1/2 theta r squared. Now see if you see what I'm getting at there. Because that's the proportion of, so this is the proportionality constant. So this is the proportionality adjustment. So now let's come back over here. If I've got this thing is the area of the difference between these two, I know that each of those original areas that I was already subtracting, if I've got theta sub k and theta sub k plus 1, what's the angle measure right there between those two? What's the difference in these two lines, their angle measure? It's this guy right here.
Just delta theta k?
Yeah, it's just delta theta sub k. It's the theta sub k plus 1 minus the theta sub k. So this angle right here is theta sub k plus 1 minus theta sub k. So that's actually my angle measurement. And I'm going to take that same proportion here. So in other words, the area of the polar rectangle, let me just write this up here and see if you see where I'm getting this from. Rectangle is the area of that full circle, that full annulus over there. So it's going to be pi r sub k plus 1, kind of got a little deficient on writing that, plus r sub k, delta r sub k, and then it's going to be theta sub k plus 1 minus theta sub k. These are measured in radians. And all I have to do to get the proportion of the whole thing that this is divide by 2. So think about it. The angular measurement divided by 2 is the portion of the full area that you would get. So now we got this nice formula here, and just like Daniel said, he called it delta theta sub k, and I'm going to do the same thing. So let's take that over here. So the area element in polar is going to be equal to, I'm going to do equal to exactly first. So r sub k plus r sub k plus 1 times delta r sub k, and then times delta theta sub k divided by 2. Now we've almost done our hard work for today, really. Because what I want to notice is when delta r sub k is small, and let's say in magnitude, r sub k must be approximately r sub k plus 1, right? The closer these two things get, the closer those radii are going to get. The smaller the chops I make, the closer these two things are going to become. So this right here, when r sub k is really small, is approximately pi times 2 r sub k's times delta r sub k times delta theta sub k over 2. Anything cool happen?
2's cancel.
2's cancel. So these two are going to cancel, and we get that this is exactly equal to, we're missing, we need to divide by another pi here. Why do we not have pi here? Hold on a second here. Let's see. Oh, I think it's, okay, so this is the full area. And I'm just thinking about these, oh, here we go. I think I thought about this a little bit wrong. So this was, put that 1/2 out front, put that 1/4 out in front there, r squared. And then this proportionality constant here would be, let's see if that's 2 pi. Wait, I'm missing. We need to divide by another pi. And for some reason, I'm not thinking of it. Oh, because the pi for the area is already included here. So once the pi is already included, and I just got my angle, right, this pi comes along for the ride. This is that same pi here. So what I need to do is move from the angle measure to this number out in front. So in other words, 2 pi needs to go to 1, pi needs to go to 1/2, and pi over 2 needs to go to 1/4, because I've already got my pi there. So what I forgot to do is put a 1 over 2 pi here. So in other words, 1 over, so just theta radians is 1 over twice 2 pi. Hold on now, it doesn't even make sense what I'm saying. Shit, I did this all at home and it made so much sense. Let's see, so 2 pi is 1. That's the multiple that I want there. So I did divide by 2 pi, and then here I divided by, oh, put the theta on top. That's it. So if theta is equal to pi, then the multiplier is 1/2. If theta is equal to pi over 2, then the multiplier is equal to 1/4. So what I'm actually trying to get here is, what is this portion out in front of the full area that I need? So I need to divide here by 2 pi as well. And then where did I do that over here? So this is 2 pi here as well. So not only do the 2's cancel, but the pi's cancel. Sorry, that probably all is just like blah, 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 blah. Hopefully it kind of made some sense. I don't think I explained it terribly well. Suffice to say that the pi I was copying down over here is already right here. So I'm just trying to figure out what portion of the full area that we had when we did this. So now the 2 pi's cancel, so we get our element is r sub k, delta r sub k, delta theta sub k. And so this is our approximate polar element. And that means that when I go to a Riemann sum and I'm adding up all these little polar rectangles, that my sum is going to look something like this. So I'm going to have double sum, I equals 1 to m, j equals 1 to n. I'm going to have some function that's a polar function, and I'm going to pick a representative. Let's draw a little picture here where this is all coming from. So this is going to be my delta r sub k. This is going to be my delta theta sub k. And then inside here, I'm picking a point r sub k star theta sub k star. That's the representative for the whole little rectangle. But then, instead of delta x, delta y here, I've got this weird thing. So I'm going to have r sub k, sorry, it's getting a little cramped in there, delta r sub k, delta theta sub k. So instead of just having, like we did with rectangular, delta x, delta y, we've got this extra variable thrown in. And it came from just the anomalies of being a polar rectangle. So as I let m and n go to infinity and get this to be perfect, it turns into a double integral over whatever my region is, f of r comma theta, whatever that function is, r dr d theta. And this is your dA when in polar coordinates. Sorry, that was a little chunky. I hope it kind of pulled mostly together. So instead of dx dy or dy dx, you use this guy. Now note that this could also be r d theta dr. So you can change the order on these two, but that r needs to be on the left side of the dr, no matter what you do. Because it's going to become an additional variable. So let's actually do a problem here. All right, so find double integral over r of x squared plus y squared dA. I don't quite know what's going to happen yet. I won't know that I need polar until I see the weird ass shape that I'm giving myself to work with. So let's do this one right here. So here's r, and let's say that goes from 2 to 3 on the radius. So the first thing I need you to do right now is, what is the range of r here? Which that one should be pretty easy. What is the theta range? To describe r. What is the range of those two polar variables going to need to be? And those are going to become the limits on our integral the minute we move to polar form. I'm going to put up a few other things that we need. Call r squared equals. We'll get to those in a minute. So can somebody tell me what's the r range here? This is not 2 to 3. There, the radius moves from 2 to 3, and then what's the theta sweep? 0 to pi over 2, right? Just up to 90. So here theta is 0 here, and theta is 90 degrees there. And erstwhile, the r is going to move from 2 to 3. So when we set up this integral, the area, or not area, just our integral, do you see why polar is perfect for this? It's literally a giant ass polar rectangle right here, right? It's just a perfect polar rectangle. These are parallel to each other in that polar sense, and then these are just little cuts on the end. Now remember these, because you're going to need them. These are the ways to transition between rectangular and polar coordinates. I set this one up to be really sweet. Because once I move to polar elements here, so here I'm going to go, all right, well, I want to use polar because of the shape of r. So for dA, I'm going to use r dr d theta, or r d theta dr. It doesn't really matter. And then out here, I'm going to have this theta correspond to the outside integral. And since theta swept from 0 to pi over 2, that's going to be my range there. And then my limits for r are just 2 to 3. That's the way those sync up. But I don't want x's and y's in here, so does anyone see any nice substitutions I could make to turn this into polar town? Yes, Daniel, what do you see?
R squared.
R squared. Notice there was still an r in there. So this r will always be incorporated into whatever else you have here. You add that in. And so now what we have is a pretty chill thing to do. I got to simplify it a little bit. R dr d theta with an r cubed inside. Let's go ahead and just work this together. So do the outside one last. And inside here, I just take the antiderivative of that. So it's 1/4 r to the 4th. R equals 2 to r equals 3. plug in those limits. So I get 0 to pi halves, 1/4, so 3 to the 4th is 81, so that's 81/4 minus 16/4 d theta. Nothing too profound going on, nothing crazy. So 81 minus 16 is 65. So that is equal to integral 0 to pi halves 65/4. I think that's right. Yeah, that's right. And then d theta. That's just a constant, so that goes to 65/4 theta. And now we're gonna let theta run 0 to pi over 2. And the 0 won't affect anything, so when I plug in pi over 2, I get 65 pi over 8. And that's the value of my integral. So the actual process is exactly like any double integral. You just got new variables. The hard part is generally moving your rectangular integral into polar form and then working it from there. But this is the essence of it. And let's just practice some. Does that sound good? We got time? We got lots of time to practice. Cool. So let me give you one. Oh, yeah. Actually, I kind of want to show you a really cool example first. So this is neat. This is something you couldn't have done anywhere else except after today. Yes, sir.
With this stuff, can you also switch like the order of integration that you do?
You can, absolutely. Yes. For these things here where they're constant, it doesn't really matter. But actually, yeah, let me give you one here. Mostly I have to give you one because I have to pee so freaking bad that I just want to just give you something to do for a few minutes here. So could you please, friends, do this integral? Double integral over r, square root of x squared plus y squared dA, and r is the unit circle. So integrate over the unit circle. And I'll be right back. You should just be able to get a nice number.
Say something about your phone dying in the middle of this?
Oh shit, thanks for the heads up. Why did you feel it die?
I just randomly thought of it.
No, that's great, Daniel, thank you. Because it's probably on the verge of dying. Let's hope it didn't die. No, not yet. Thanks to you, we will make it.
What percentage is it at?
What percentage is that on your grade?
No.
Oh, oh okay, let's see.
Probably like
I was like, wow.
60% for
You don't do it for free, do you? I can't see. Unfortunately, I can't see without screwing up the recording.
Yeah.
I wish I did know though. See where you're at. Yeah.
See when my spidey senses went off.
Yeah, exactly. I think you were pretty close. Because it was damn close to dead.
Yes.
Thank you so much. That saved a lot. So Daniel, here you could do dr, d theta, or d theta, dr pretty interchangeably. I'll show you an example where order would be really important that we couldn't switch it. All right. So I'm just gonna go with the classic. What does this turn into here?
R.
Just r, right? That is the square root of r squared, so that is literally just r. And then here we're gonna tack in r dr d theta. And since I did write r on the inside integral, I'm gonna let r sweep from where to where?
0 to 1.
0 to 1. We have to make sure we hit every possible spot along the radius. So 0 to 1, and then what's my theta sweep?
0 to 2.
0 to 2 pi, it's full circle. And then, you know, we can work this through. I'm not gonna work it through. We got the integral set up, we're good to go. Unless someone wants to see it work through, I'm happy to do that. But I kind of have something really cool I wanna get to. Everybody feeling good on this? Yeah? Yeah. Cool. So, does this, where have you seen this integral before? Maybe nowhere. Has anybody done like probability with?
Isn't it like 1 over 1 plus tangent?
I've seen it.
It's gonna be square root of pi. It's gonna be the answer to give a spoiler, but it's how we get there. Yeah. Have anybody done probability with the normal distribution? If anybody, you've probably done that, right? Where you've got the bell curve. So this thing here, if you sketch out y equals e to the negative x squared, you get exactly a normal distribution with a certain, I don't remember exactly what the standard deviation is here and stuff, but you get that curve. So what we're actually asking is, how do I find the area underneath that thing? That's what this represents. So watch, this is a cool trick. I remember I first saw this, I think, in Calc 3, back in junior college a long time ago. A really awesome calc professor. So we're going to do a trick here. Let's just call this I right here. You know there's a trick coming when you label your integral with a variable. There's going to be some funny business going on. So I squared is equal to this integral times itself, because that's just some number. And when I write the second one, with this variable of integration doesn't matter. So I'm going to use y on this one. Write it like that. Because this is the same thing as this, just with a different letter. So that's I squared. But now that I did use these independent variables, I can kind of bring this thing together, because this is a constant, right? This is a constant with respect to this one and vice versa. So I could bring it inside, and out in front, I'm just going to have integral infinity. So I'm going to bring this guy in. And then I had this e to the negative x squared dx. Just bringing it in like a constant. And then I'm going to play a funny game here where I just kind of get rid of these parentheses and move that dy over there. Think about how Riemann sums work. This is like a delta y, this is a delta x, so it shouldn't matter when I'm summing all these things up if I do it here or outside. So in other words, this becomes double integral minus infinity to infinity, e to the negative y squared, e to the negative x squared, dy dx. Make sure that's you're following. Nothing funky yet, but I can combine these two. I can add those exponents because we have a common base. So I've got integral negative infinity to infinity, e to the negative and I'm just gonna do a little bit of fancy work, the negative quantity x squared plus y squared, and then here we can do dy dx, doesn't really matter. Does this sound okay? What is the region we're integrating over? So my goal is, see this x squared plus y squared, that's like begging to be replaced with r squared. So I want to move this to polar form, but where are we integrating? What is that region? What's the region of integration?
The inverse tangent of 1.
Well, no, so tell me how you're thinking about that.
I was trying to convert the infinity, negative infinity to.
Okay. So let's do that. Let's do that together. The x coordinate runs anywhere from negative infinity to positive infinity. So it can have any x coordinate and should have all x coordinates. The y coordinate can also be anything. So what did I just describe if I say all possible x coordinates and y coordinates? Whole plane. This is saying your x runs from negative infinity to infinity, erstwhile your y runs from negative infinity to infinity. So this region right here is equal to the entire plane, R2, the full plane. Does that make sense, Cormac? Yeah. You were getting way too fancy with it, yeah. That's cool though, I like it. Anytime I hear an arctan that I didn't bring up, I'm happy. So what are the polar, we're trying to redo this thing now, right? So now we're gonna move it into this state, so it's over the entire plane, e to the negative x squared plus y squared, dA. Let's move to polar now. So this becomes e to the what?
Negative r squared.
Negative r squared, because that's x squared plus y squared is r squared. I'm going to tack in my r dr d theta. One thing I should note right up front, and we kind of talked about that the other day, is you cannot do this. This can't be done, right? Remember that, because we can do this, and we can do this integral, but if u is negative x squared, du is negative 2x dx, you would need an x in there. So you can't do this by hand in rectangular form, but look what happened when we moved to polar. We got that r outside. That's going to be like the differential. That's going to be like, that's u, that's close to du, just off by a multiple. So if I want to describe the full plane, what radii do I need? What's the minimum radius? 0. Start at 0. What's the full radius I need?
2 pi.
You're thinking theta. So that's good. I agree with that. Full revolution. What about radii? Distance from the origin. Infinity. So now I got this integral in polar coordinates, and this should be the exact same value as that. And the only difference is we can do this one. So let's do this one. So this is going to be integral 0 to 2 pi. And remember, this is the square of the thing we're looking for, but it's okay. We'll just take the square root of it when we get it. And then this stuff inside here is just 1/2 e to the negative r squared. And I'm going to cheat and write 0 to infinity, even though it's kind of a limit. Let me stop for a second. Tell me if that makes sense. I made a fast move there. I don't usually move that fast. Do you see how I got there? Kind of like did a substitution in my head kind of thing, right? If you took the derivative of this, you would get a negative 2r. Oh, sorry, this is negative 1/2 out in front. If you took the derivative of this, you'd get a negative 2r that came out in front, and then that would cancel with that and give you a good old r there. This is negative 1/2 e to the r squared. So when I plug in infinity, this bottom blows up and the whole thing goes to 0. So this is equal to integral 0 to 2 pi. Plug in infinity, you get 0. minus -1/2, now I'm gonna plug in 0 again, e to the 0, e to the -0 squared, when I put that in for r, d theta. Look what we got here, we get 0 to 2 pi times, there's a half that comes out in front, e to the 0 is 1. Oh my God, so beautiful. This is just 1/2 times 2 theta minus 0. Or excuse me, 2 pi minus 0. So the answer is just pi. So pi is I squared. So I squared is pi. Therefore, this integral here is the square root of pi. And so that's something we couldn't have done any other way. Besides, well, you can't do it exactly any other way at all. So that's quite beautiful. Let me give you one to do now. That was kind of for me, but like I wanted to share it with you all because it's just too cool. See, I got some notes over here. I think I got something cool for us to do. Yeah, I do. Oh, a density problem. What a weirdo. All right. Made up a density problem for us. So we're gonna find the mass of something given a density, but it's going to be not the kind of thing you want to do in rectangular coordinates. Kind of putting together what we did last time with today. So find the mass of a disk of radius 2 centered at the origin if the density delta xy is given by 1 over x squared plus y squared plus 1. How do we do that? Let's first set it up. And we'll call this circle R. So that's 2. That's our circle. Then we'll call that whole thing R. Let's set it up in rectangular coordinates because that's the way this was given here. So I've got double integral over R, the density function, and then I would have my area element here, dA. Let me let you take it from here. Convert to polar, find the value. I think I can even tell you the value so you can get a quick sanity check on yourself. What the hell, are these my notes? What is going on here? It looks totally alien. Okay, there we go, there's some polar shit. That's good. The answer should be pi natural log of 5.
I guess it is 1 over.
Yeah. What's that?
It's 1 over that. So
It is 1 over,
natural
yeah,
logs.
yeah. What is this disk like in terms of density? Where's it the densest?
Is it like slightly off from the center? Should be
Oh, I see, because you're thinking of the +1. It actually still is at 0, 0. Because think about this is actually r squared right here, right? In polar form, there's a little hint, it should turn into that. So as r increases, the density decreases. But it's most when r is 0. That +1 keeps us from blowing up to infinite density. So its densest here, it becomes lighter as we move out toward the edge. I'm gonna try to have some take-home skill checks for you on Friday. Bring in a bunch and just let you have some time with them.
recheck, your integral should look like this. Make sure your limits all look good. Questions?
How does it integrate from 0 to 1, not 0 to 2?
Oh, sorry, you're right, thanks, I forgot it was radius 2. That's a great question. It doesn't. Thank you.
Little substitution practice. Reminder, the basic form there. Kind of got it all up there.
Just make sure you can do this. And if there's anything up there that looks weird or confusing, let's talk about it. Bless you.
Thank you.
Look reasonable. Seeing some head nods.
Weird answer. Natural log of 5 is a weird thing to see. Check that out. I'm gonna get something else written up here. Last one, gotta address Daniel's point fully about switching the limits. And plus teach you a little bit more about polar coordinates. All right. Let me just make sure, is there anything I can do to help clarify what just happened? Good.
It's just phase shifted over. Is it?
Yes, definitely. If we were like in XY plane, we would think of this as a phase shift, absolutely. Just a shift over this way. What actually is the area of A? If that's a circle, what is the area?
It's 1/2 pi r. Just
What's the radius?
1/4 pi.
1/4 pi. Yeah. So you see here, if this is a perfect circle, the center is at 1/2. So the radius is 1/2. So we know that A is pi times the radius squared, so it's pi over 4. We kind of know, we can figure that out anyway. But we're not here to do things the easy way. We're here to exercise our mathematical abilities. So what I want to do is do that in polar form. Now you might think, oh shit, I don't know how to do that circle in polar form. Well, I'm going to help you. So polar equations are kind of weird. The equation of that thing is, I think it's definitely that, r equals the cosine of theta, and I want to explain why that is so. So I'm going to show you a couple ways to convince you that if this was in polar coordinates, r theta, that the graph, the set of all r and theta that satisfy this equation look like that circle right there. So let me show you first off an algebraic way. I'm going to multiply each side by r. So I get r squared equals r cosine of theta. Does r cosine of theta ring any bells from those conversion formulas that I put up a little bit ago? That is x, exactly. So that's x. What is this in terms of x and y? X squared plus y squared. Starting to look circly. Yeah. So let me get everything to the left side. So this is going to be x squared minus x. I'm going to leave a little space here because I'm about to complete the square. Plus y squared equals 0. I want to turn this into x minus something so that the outer and inner, the FOIL, you know, when you do FOIL on this, I want the outer and inner to add up to negative 1x. So what you do is you take half this coefficient here, which is negative 1/2, and add that on as a square. So right now I'm just completing the square. You have to add that to both sides, otherwise you've changed your formula. So then this just turns into x minus 1/2, quantity squared, plus y squared equals 1/2. Let's put 1/2 squared there. A circle with a center. So you may or may not remember this, but if I gave you x minus h squared plus y minus k squared, whoop, square goes out there, equals r squared. This is a circle of radius r centered at hk. Good thing to know. It's a shitty circle, but get the point, hopefully. So this is a circle centered, here we have h is 1/2 and k is 0. So it's a circle centered at 1/2 comma 0 of radius 1/2. Works out. So I can do this algebraically and see it. Let me show you another way, like an intuitive way to think about the flow of r versus theta. So when I haven't taught like pre-calc in ages, but when I have, I've never actually seen anybody explain polar graphing the way I have. But it's because as a young nerd, I just spent so much time doing it for recreation that I came up kind of with my own system for doing it. So let's see here. So I've got r equals cosine of theta. So you can think of this, let's pretend for a minute we're in rectangular coordinates, and that's just y versus y equals cosine of x. And plot this like I'm in rectangularville. So step one is, well, I'm not going to write out a step-by-step thing because that'll end up weird. But it's just a good old cosine graph, so goes like that. And of course that continues on, but let's just get one period's worth out here. That's 1, that's minus 1, that's pi halves, and that is raised pi over 2. All right, so now I can look at this rectangular graph and understand the relationship between the radius and the theta. Now I want you to think of it this way. I'm just some dude with a fishing line, and I'm standing at the pole. I'm standing at the origin, 0, 0. And r is the distance I've cast out. And theta is the angle I'm at with that cast length. Does this kind of make some sense? So I've just got this wire that I'm changing sides with, or changing size of. So first off, let's just think theta is 0. So let's say that's this way. And in fact, that kind of makes sense, right? Because theta equals 0 would be straight out that way. I'm going to cast my line out to its full extent, 1 unit. So like right now, I'm going to give this to Daniel. Can you hold that for me? That's where my hook is. So I got this cast out full length. Now as I rotate to 90 degrees, what do I do with my reel? I'm going to pull it in. So as I rotate this way, thank you. I guess I could have done it like this. It just had to be extreme, I guess. So right here, here's my radius all the way out to 1. As I rotate to 90 degrees, so turn a full 90 degrees, I reel in my line. And when I'm facing away from you, this line, I don't have any thread out. Do it again. Here's full cast. Pull it in. But now what happens is I rotate the rest of the way. So I keep rotating, but now I've got negative radius. So as I start to rotate this way, I'm casting behind me, and it's extending all the way out until I get to 180 degrees, in which case I'm back at a full -1, which got me back to where I started. Does that even make sense, what I'm saying there, kind of? Eric, does that make sense? Mm-hmm. Yeah, okay, cool, all right. Had to check. So here's what happened. When theta was 0, I had my full casting all the way out. As I rotated up to 90 degrees, I pulled the cast line in. Once I'm facing over here, so now I'm actually facing this way in this piece right here. This is pi over 2 to pi, but the radius becomes increasingly negative. So as I sweep here, so like as I'm facing in this direction, I'm actually casting out behind me. And so I do that from 0 to a full 1 again. So this actually does the full circle. That's one full trace of the circle from 0 to pi. And then when I do it again, I'm actually double tracing this thing. So if I were to keep, so like right now, I'm at 180 degrees facing this way, but I'm cast out this way. As I keep rotating, it just comes back in again, and I retrace, and then I come around, and it comes back out again. So if I went the full 2 pi, I would trace this thing twice. If we were actually studying this stuff, we'd spend a lot more time practicing this, but that's one way to look at it. So when I integrate this thing, I don't want to integrate 0 to 2 pi. I want to integrate from, so here's theta equals 0, here's theta is a quarter, here's theta is 3, or theta is getting close to half, here's theta is exactly pi over 2, here's theta moving from pi over 2 to pi. So what I'm saying here is that I want to make sure my theta just runs between 0 and pi, otherwise I'll double the area. I don't want to count the thing twice. So now let's do this. Let's get our integral up. No, well, we're almost there. We're almost there. So I'm going to do integral over that region A, that circle, of just my area element. This should be the area of A. You just have a 1 here as your density. Hopefully you kind of remember that. So then this is going to be over A, and here I'm going to put r dr d theta, because that's my area element in polar. There's a secret 1 right here. Now theta, I just want to run from 0 to pi so I don't double trace it. But what is happening to r? So now here, Daniel, this is kind of like the r has to be on the inside, because I have to pick a certain theta. So here's a fixed theta. And then I have to move the reel from everywhere from 0 all the way up to the maximum radius I could have here. So for each theta, the range of r is going to change. When theta is 0, r runs from 0 to 1. When theta is 45 degrees, pi over 4, then you're going to have a slightly less r. But you just have to remember that the radius is exactly equal to the cosine of the angle you're looking at. So r here is going to run from 0 to the cosine of the theta. And we're going to crank this sucker out. Hey, could you do that sucker, please? That's good practice. This is your home stretch. You got like 5 minutes left. You can do it.
So does R always start at the origin then?
Yes, unless I had somehow decided, like, there might have been something weird, like we had this other circle that made sure, so like, if this was a circle of radius 1/2 right there, then I would start at 1/2 and go all the way out.
Okay.
So it could get a little weird if I had a little crescent moon shape there.
Okay.
Does that make sense?
Yeah.
So yeah, it does always go from 0 on out for this particular, I think that's what you're asking probably, just for this guy, yes. Oh, I'm curious to see what happens here. This is good. I'm very excited to see how this integral turns out, see if anyone remembers how to do it. Does anybody remember how to do that? I kind of have a hint up there, but we need to work it through. Does anybody remember how you take this cosine squared and integrate it? Because you can't do it the way it's written.
It's an identity, right? It's like the,
is.
It's not the double angle, is
It is kind of, yeah, exactly. Well, you're going to remember it now. That's it. That's a great start. So this identity here is so helpful. If you say cosine of 2 theta, you can first write that as cosine of theta minus sine squared of theta. And then we also know this beautiful, I'm like, this is just one of the greatest things ever. And this will like hit you everywhere in life if you're a technical person from at some point or another. This is a great thing to know. If I take this, I could rewrite it as cosine squared of theta equals 1 minus sine squared of theta. And then I could replace this cosine here with 1 minus sine squared of theta, and then I already had minus sine squared of theta. So another version of this formula is 1 minus 2 sine squared of theta. But I could have also taken this thing and solved it for sine squared. And in which case, I would be replacing this sine squared here with 1 minus cosine squared theta. So that would give me equals, and you can probably believe this, 2 cosine squared of theta. That's the other form. So 3 beautiful forms. This one here, if you remember this, and remember this, you can get this guy or this guy at your whim. Always good to be able to build that stuff. So now, this is what Christian was remembering. This allows me to replace a cosine squared or a sine squared with something that's not squared, but will require a little substitution. So here, because I have cosine of 2 theta equals this, add 1 to each side, cosine of 2 theta plus 1, and then divide by 2, and that is cosine squared of theta. So that's how we do this guy. We actually sub in, this is 1/2 integral 0 to pi. I'm gonna rewrite that as 1/2 1 plus cosine of 2 theta d theta. And then we just work this through, just to save some time, I'll just tell you, and you shouldn't be surprised, the answer is pi over 4. And it better be, because we already know the area of this circle is pi over 4. But that's how you do that integral. So, friends, there's some web works up if you want to practice this stuff. I have a feeling most people will start practicing it when it's required on the sheets that I give you on Friday. This Friday is our last Friday we're going to meet in person. Let me explain why. So this Friday, we'll be meeting here, doing stuff. Next Friday, I'm going to be at a conference at CU. But I will record a lecture. So there will still be class, but it'll be asynchronous, and you'll do it on your own time and watch that. The following Friday is, what is the following Friday? What is it?
Good Friday?
Good Friday, yeah. So we're not here on Good Friday, which is great, right? That's cool, we get a break. The final Friday of the semester is going to be math on the quad day. How many people have done math on the quad day? Awesome, cool. So math on the quad day, you will have an assignment. I will be out on the quad with shitloads of chalk, covered in chalk, being a spaz, trying to rally people in. I will give you a problem to work. You will come work it on the pavement in chalk, and that will be your skill check or something like that. Doesn't have to be artistic, but the more colorful it is, the warmer my heart gets. So this Friday's our last Friday. It's needless to say. Thank you, friends. I can't believe we're at the end. But it is starting to feel kind of good. You probably are all starting to feel more stressed out, right? Because you got like, I don't know how you feel. Camille, how are you feeling? Are you feeling like the space or like?
I'm feeling like I'm already done.
Yeah, I'm there with you. Yeah, feeling done. There we go. Also, please check the grade book for the love of all that's holy. Check your scores and make sure that stuff's recorded, okay? Please. That's on you.
So we did.
Thank you. Mr. Othman, hold on a second, my friend. Hi. So have you checked on, have you gotten a hold of anybody? Because we have to, that's the first thing. And what did they say?
I'm waiting for
You're waiting for,
you to remove the home, no? So
no. You're waiting, no, I can't do that. But I had asked you to call the.
We're talking about the credit?
Yeah, the credits.
Oh,
Yeah,
sorry.
Wait, you haven't been able to register?
No, not
Oh,
yet.
shit.
Oh.
Okay, yeah.
that's-
I will take care of that.
sorry.
Right, I didn't realize that.
Yeah,
didn't
I
even
sent an
realize
email
that.
and they told me they're gonna get it back to me tomorrow.
Okay, thank
I'll
God.
let you know.
Okay, cool. Yeah, I will issue flags immediately. I didn't even realize that was a problem.
Yeah.
Sorry. I think we've been communicating about things and I've been thinking it was something
And
else.
it's working, covered, do the.
Yeah. Can you come
yeah,
in
I'll
at
come
around
down.
11?
11, yeah.
Okay.
Yeah.
Awesome. I'll see you tomorrow at
Thank
11.
you.
That sounds good. And maybe we'll know about your
Yeah.
credits and stuff by then.
Thank you.
Well, thank you.
More corrections.
Oh, thank you, sir. Beautiful. Appreciate it. Thank you, sir. Love it. Question?
Question. Yeah,
Awesome. Sounds
So
cool.
this, for the one where we had the 2 and 3 and
Yeah, yeah.
we got this for the integral, but doing it like geometrically, I'd get this, right?
Huh. Well, let's see. That's a great question. Well,
Yeah.
let's find out. Oh, wait. You would, except that we had an integrand.
Oh.
You're
yeah.
so right. But that integrand upped the value
Okay.
significantly. But I like that you're looking at it and thinking, does this make sense?
Because I was like, that seems so much easier just to do the geometric.
Yes, definitely that would be the easy way, yes. Hi.
Hi, I have a question.
Yes, ma'am.
So I know we like said that there was no due dates, but then we also
Of
said
course.
that I would send it to you.
Yeah,
on
I mean,
Friday.
that was just like, to give you some kind of structure, but
Okay.
whatever you need, Kayla.
Cause we
I'm gonna
did-
come around this.
No, you're good. We have an OChem exam Monday.
That's
I
what's
was-
important.
Yeah, I was
Yeah.
wondering if I could turn it in like sometime
Of
after that.
course,
Okay.
yes, you can turn it in never, and everything will be okay.
Okay.
But yeah, I was just like giving you like
Some kind of, yeah.
some rough structure,
Okay.
but the structure should always be second to your actual business.
I just wanted to make sure. I should be able to get it to you next week.
It's cool. Is the book? Are you able? Is the reading the book working?
Yes, everything's working with that.
Okay, it's a pretty good book.
It is.
Okay,
I'm enjoying
awesome.
it so far.
Oh, cool. Okay, that's excellent.
Yeah.
Yeah, you take your time.
Okay, thank you.
You're
I just
welcome.
wanted to like.
Yeah,
make
yeah, I
sure.
appreciate that.
Okay, thank you.
Thanks, Kayla.
Have a good rest of your
You
day.
too. Take care. Oh God.